Now we are going to discuss the continuation of our topic. Define the basic quantities and variables such as mass, weight, acceleration, force, volume, and density. How do you find the mass when a given volume and density? Density calculator uses the formula P equals or pressure equals mass over volume, or density pressure is equal to mass divided by volume, and the calculator can use any of the values to calculate the third. Density is defined as per unit volume. What is mass? Mass is a measure of the amount of matter in an object. Mass is usually measured in grams, kilograms. Mass measures the quantity of matter regardless of both its location in the universe and the gravitational force applied to it. Your mass on the Earth and the Moon are identical. The mass of the body is the measure of the amount of material present in the body. The weight of the body is the force exerted by the body when its mass is accelerated in gravitational field. Acceleration is the rate of change of velocity with time. An object accelerates whenever it speed ups, slows down, or changes direction. Now let us take a look the video explaining the mass and weight.
Welcome to Moo Math and Science. In this video, I'd like to discuss, doesn't mass and weight measure the same thing? Close, but not really. The mass of an object is a measure of the number of atoms in it. The SI unit for mass is the kilogram. Weight is a measure of the force that gravity is pulling on the same object. Gravity is a force and technically should be measured in newtons. A newton, represented with capital N, is equal to the acceleration of 1 kilogram, 1 meter per second. Your weight can change based on the gravitational pull of your location. For example, you weigh less on the moon than on Earth. The weight of a candy bar that has a mass of 101 grams exerts a force of 1 newton when held in your hand. When you step on a scale, it is an accurate measure of your mass, but an estimate of the force of your weight that is exerting on the scale. To find out how much force a 100 kilogram dog exerts on the scale, just multiply by 9.8. and that equals 980 newtons. So in conclusion, mass is a measure of how much matter something contains, and weight is a measure of how strongly gravity pulls on the same object. The SI unit for mass is kilograms. The SI unit for force is newtons. Thanks for watching, and Moo Math uploads a new math and science video every day.
We will look another video explaining both mass and weight.
what's up, guys? We saw in the last section temperature and a little bit about heat. Now it's time to make sure that you know the difference between weight, pressure, and force and gravity. First things first, what's mass and what's weight? It's very typical that people confuse mass and weight. Actually, many people will tell you, I lost 5 pounds. And they will tell you that that's their weight. But actually, losing 1 pound is mass. And weight will be another stuff that we are going to take care here. Mass is the amount of matter, essentially. How much stuff, how much material do you have? So one human will be probably, I don't know, let's say this girl is about 56 kilograms. That for you guys that are into the English system, it's about 100 pounds. This girl, if she's in the moon and if she's in Earth, she's still 100 pounds because, I don't know, all the body is the same. Hopefully you know that all the body is the same, even though she's in the moon or in the Earth. Now, when we speak about weight, we talk about the accelerated mass due to gravity. So you have, force equals mass times acceleration. In this case, one special type of force is weight, which is the mass times the gravity. Gravity is an acceleration, weight is a force. Mass is still mass. So even though the mass is the same, we know that the gravity on the Earth is not the same that on the moon. Actually, in the moon, it's 1/6 of that of the Earth. So probably she's 56 kilograms here. She's 560 newtons in the Earth. And if you wanted to measure that weight on the moon, you will see that she's way lighter because you need less force to, let's say, carry her. She will need actually 90 newtons to carry her. When in the Earth, you will need 560 newtons. But the mass, guys, is the same. We're talking about forces, not mass. So just be sure about that. A mass of an apple in the Earth is 0.1 kilograms. Weight of an apple in Earth will be that mass times gravity, which will be 0.1 kilograms times that gravity, 9.8 meters per square second, which is about 1 Newton. The weight of an apple in the moon will be mass times gravity once again. The mass is the same, doesn't change. The gravity does change because it's another planet, and it will be 0.16 newtons. So hopefully you know by now that mass and weight are not the same. What's up?
We will watch another video explaining mass and gravity.
Most of us have seen images of men walking on the moon. Now, even though the astronauts are wearing really heavy suits, they seem to bounce around the surface of the moon with very little effort. How is it that we can bounce around on the moon with ease while jumping?
Welcome to Moo Math and Science. Welcome to Moo Math.
Now it's time to make sure that you know the difference between weight. Probably she's 56 kilograms here. To know if you're like in the videos, because it's another planet, and it will be 0.16.
Most of us have seen images of men walking on the moon. Now, even though the astronauts are wearing really heavy suits, they seem to bounce around the surface of the moon with very little effort. How is it that we can bounce around on the moon with ease, while jumping here on Earth requires a lot of effort? The answer to this question lies within the difference between mass and weight. Mass is a measure of how much matter an object contains, while weight is a measure of the force of gravity on the object. An object has the same composition and therefore mass regardless of its location. For example, a person with a mass of 70 kilograms on Earth has a mass of 70 kilograms in space, as well as on the moon. However, that same person's weight is not the same since gravity is different in these locations. The person will weigh less on the moon because the moon has less gravity. To better understand the concepts of weight and mass, we must first consider gravity and its effect on objects. So what is gravity? Gravity is the attractive pull between two objects that have mass. The strength of gravity is directly proportional to the amount of mass of each object. In other words, the larger the objects, the greater the gravitational attraction between them. For example, the gravitational pull you experience on Earth is much greater than it would be on the moon, because the Earth's mass is greater. An object with twice as much mass will exert twice as much gravitational pull on other objects. On the other hand, the strength of gravity is inversely related to the square of the distance between two objects. For example, if the distance between two objects doubles, meaning they're twice as far apart, the gravitational pull decreases by a factor of 4. This is because 2 squared is equal to 4. This means the effective distance on gravitational attraction is greater than the effect of the masses of the objects. Gravity is a force. A force is simply a push or pull experienced by objects that interact with each other. The interaction can be direct or at a distance, which is the base of gravity. Newton's laws tell us that if an unbalanced force acts on an object, it will change the object's state of motion. In other words, the object will accelerate. Since gravity is a force, gravity causes objects to accelerate. Let's look at an example of how gravity causes acceleration. If you drop a ball from a cliff, you'll notice that the speed increases as it falls. It accelerates due to gravity. We have determined that the acceleration of gravity is 9.8 meters per second squared. That is for free-falling objects on Earth. Free-falling simply means no other forces except gravity are acting on the object. For example, any effect of wind resistance would be neglected. The velocity of a free-falling object increases by 9.8 meters per second every second. Let's look at the speed of the ball as it drops over time. This is going to help us understand how gravity causes acceleration. As you see on the screen, the ball will accelerate to a speed of 9.8 meters per second in the first second of travel. Over the next second, the speed of the ball will again increase by 9.8 meters per second, meaning it's traveling at 19.6 meters per second. The same thing will happen during the third second of time, so the ball will be traveling at 29.4 meters per second. With each second, the ball's speed increases by 9.8 meters per second. The acceleration of gravity is so important, it has its own symbol. It is often abbreviated with the letter G. G is equal to 9.8 meters per second squared. That's the acceleration of gravity.
Let us take a look at another video explaining the mass and gravity.
simply means no g.
So let us proceed to acceleration. We will watch the video explaining the acceleration.
When we are in a stationary car that moves rapidly to gain speed, we get pushed back against our seat. And when brakes are applied, we get pushed ahead. Or when we take a sharp right turn, we're pushed towards the left. These are all situations where we are accelerating. We have all experienced this, whether in a car or a bus or while riding a motorbike. Simply put, when velocity changes, we have acceleration. I still haven't defined what acceleration is. I just told you that when velocity changes, there will be acceleration. Okay, let me give you two examples. In the first one, a car is traveling in a straight line at a constant speed of 80 kilometers an hour. And in the second one, a plane is traveling in a straight line at a constant speed of 1000 kilometers an hour. In which case do you think acceleration is involved? None. In both cases, the velocity is not changing at all. Hence, there will be no acceleration in either of the cases. Most people relate acceleration to high speed, and that's clearly not true. Acceleration will only exist when there is change in velocity. Do you remember what velocity is? It's speed with direction, and it's hence a vector quantity. Why is this important? Let's say a body moves from rest and reaches a velocity of 20 kilometers an hour in 5 seconds. Will acceleration be involved here? Yes, because the velocity is changing. It was 0 initially, and at the end of 5 seconds, it's 20 kilometers per hour. In another scenario, assume that a body is moving at 30 kilometers an hour, and then it moves right at 30 kilometers an hour, and continues traveling at the same speed of 30 kilometers per hour. Will there be acceleration in this case? The answer is yes. As the direction is changing, the velocity will also change. The only thing constant in this example is speed, but the velocity changes as the direction changes. So this was the most important concept you had to know about acceleration. It will exist only when there is a change in velocity. But how is acceleration calculated? Acceleration is defined as the rate of change of velocity. In terms of a formula, acceleration can be written as change in velocity over the time taken. If the velocity of an object changes from an initial value of u to the final value of v in time t, then the acceleration a can be written as v minus u over t. Say this object is at rest initially at point A. It then travels to the right and attains a velocity of 10 meters per second in 5 seconds. What will be the acceleration here at point B? We can look at the formula to get the answer. The initial velocity u is 0 meters per second as the object is stationary. The final velocity v is 10 meters per second and the time taken t is 5 seconds. Hence the acceleration a will equal 10 meters per second minus 0 meters per second divided by 5 seconds. So this will equal 10 meters per second divided by 5 seconds. 10 divided by 5 is 2. Wait, hold on. What will be the units of acceleration? We should get a hint by looking at this. The units of acceleration will be meters per second, because it's the change in velocity over the time taken. As this is meters per second, we can carry this second to the denominator, and what we will get is meters per second squared. This one is more intuitive, but this one is a bit neater, I would say. So the acceleration in this case will be 2 meters per second squared. And acceleration is also a vector quantity. Here, acceleration and velocity are in the same direction. There are many more important concepts about acceleration which we will cover in the coming videos.
So we'll watch another video explaining the acceleration.
In this video, I want to talk a little bit about acceleration. Acceleration. And this is probably an idea that you're somewhat familiar with, or at least you've heard the term used here or there. Acceleration is just the change in velocity over time. Change in velocity. Velocity over time. Probably one of the most typical examples of acceleration, if you're at all interested in cars, is that many times they will give you acceleration numbers, especially for sports cars. Actually, all cars. If you look up in Consumer Reports or wherever they give the stats on different cars, they'll tell you something like, I don't know, like a Porsche, and I'm going to make up these numbers right over here. So let's say that we have a Porsche 911. Porsche 911. They'll say that a Porsche 911, they'll literally measure it with a stopwatch, can go 0 to 60 miles per hour, and these aren't the exact numbers, although I think it's probably pretty close, 0 to 60 miles per hour in, let's say, 3 seconds. In 3 seconds. So, although officially what they're giving you right here are speeds, because they're only giving you magnitude and no direction, you can assume that it's in the same direction. I mean, we could say 0 miles per hour to the east to 60 miles per hour to the east in 3 seconds. So what was the acceleration here? So I just told you the definition of acceleration. It's a change in velocity over time. So the acceleration, and once again, acceleration is a vector quantity. You want to know not only how much is velocity changing over time, you also care about the direction. It also makes sense because velocity itself is a vector quantity. It needs magnitude and direction. So the acceleration here, and we're just going to assume that we're going to the right, 0 miles per hour and 60 miles per hour to the right. So what is it's going to be change in velocity. So let me just write it down with different notation just so you can familiarize yourself if you see it in a textbook this way. So change in velocity. This delta symbol right here just means change in velocity over time. Over time. And it's really, as I've mentioned in previous videos, it's really time is really a change in time, but we could just write time here. This 3 seconds is really a change in time. It might have been, if you looked at your second hand, it might have been 5 seconds when it started, and then it might have been 8 seconds when it stopped. So it took a total of 3 seconds. So time is really a change in seconds. But we'll just go with the time right here. So, or we're just with the t. So what's our change in velocity? So our final velocity is 60 miles per hour. Our final velocity is 60 miles per hour. And our original velocity was 0 miles per hour. So it's 60 minus 0 miles per hour. And then what is our time? What is our time over here? Well, our time is, or we could even say our change in time. Our change in time is 3 seconds. 3 seconds. So this gives us 20 miles per hour per second. Let me write this down. So this top part is 60. 60 divided by 3 is 20. So we get 20, but then the units are a little bit strange. We have miles. Instead of writing mph, I'm going to write miles per hour. That's the same thing as mph. And then we also, in the denominator right over here, have seconds, which is a little bit strange. And as you'll see, the units for acceleration do seem a little bit strange, but if we think it through, it actually might make a little bit of sense. So miles per hour, and then we could either put seconds like this, or we could write per second. And let's just think about what this is saying, and then we could get it all into seconds, or we could all get into hours, whatever we like. This is saying that every second, this Porsche 911 can increase its velocity by 20 miles per hour. So its acceleration is 20 miles per hour per second. And actually, we should include the direction because we're talking about vector quantities. So this is to the east. So this is east, and then this is east right over here, just so that we make sure that we're dealing with vectors. You're giving it a direction, due east. So every second, it can increase in velocity by 20 miles per hour. So hopefully with the way I'm saying it, it makes a little bit of sense. 20 miles per hour per second. That's exactly what this is talking about. Now, we could also write it like this. This is the same thing as 20 miles per hour, because if you take something and you divide it by seconds, that's the same thing as multiplying it by 1 over seconds. So that's miles per hour, seconds. And although this is correct, to me this makes a little less intuitive sense. This one literally says it. Every second, it's increasing in velocity by 20 miles per hour. 20 miles per hour increase in velocity per second. So that kind of makes sense to me. Here it's saying 20 miles per hour seconds. So once again, it's not as intuitive. But we can make this so it's all in one unit of time, although you don't really have to. You can change this so that you get rid of maybe the hours in the denominator. And the best way to get rid of an hour in the denominator is by multiplying it by something that has hours in the numerator. So hour and seconds. And here, the smaller unit is the seconds. So it's 3,600 seconds for every 1 hour. Or 1 hour is equal to 3,600 seconds. Or 1/3600th of an hour per second. All of those are legitimate ways to interpret this thing in magenta right over here. And then you multiply. Do a little dimensional analysis. Hour cancels with hour. And then you have, this will be equal to 20 over 3,600. 20 over 3,600 miles per seconds times seconds. Or we could say miles, let me write it this way, miles per seconds times seconds, or we could say miles per second. I want to do that in another color. Miles per second squared. Miles per second squared. And we can simplify this a little bit, divide the numerator and the denominator by 10. You get 2 over 360, or you could get this is the same thing as 1 over 180 miles per second squared. I'll just abbreviate it like that. And once again, this doesn't make, 1 and 180th of a mile. How much is that? You might want to convert it to feet. But the whole point in here is I just wanted to show you that, well, one, how do you calculate acceleration, and give you a little bit of a sense what it means. And once again, this right here, when you have second squared in the bottom of your units, it doesn't make a ton of sense. But we can rewrite it like this up here. This is 180, or 1 over 180 miles per second, and then we divide by seconds again, per second, or maybe I could write it like this, per second, where this whole thing is the numerator. So this makes a little bit more sense from an acceleration point of view. 1 over 180 miles per second. Every second, this Porsche 911 is going to go 180th of a mile per second faster. And actually, it's probably more intuitive to stick to the miles per hour, because that's something that we have a little bit of more sense on. And another way to visualize it, if you were to be driving that Porsche and you were to look at the speedometer for that Porsche, and if the acceleration was constant, it's actually not going to be completely constant. And if you looked at the speedometer, let me draw it. So this would be 10, 20, 30, 40, 50, 60. This is probably not what the speedometer for a Porsche looks like. This is probably more analogous to a small four-cylinder car's speedometer. I suspect the Porsche's speedometer goes much beyond 60 miles per hour. But what you would see for something accelerating this fast is right when you're starting, the speedometer would be right there. And that every second, it would be 20 miles per hour faster. So after a second, the speedometer would have moved this far. After another second, the speedometer would have moved this far. And then after another second, the speedometer would have moved that far. And the entire time, you would have kind of been pasted to the back of your seat.
So we'll continue. In thermodynamics, a thermodynamic force is a system based on quantification of energy tendencies. In a sense, the thermodynamic force is the energetic description of the driving force of any process. As stipulated by the first law, the total energy of the system and its surroundings is conserved. In thermodynamics, the volume of a system is an important extensive parameter for describing thermodynamic state. The specific volume in an intensive property is the system volume per unit of mass. The physical volume of a system may or not coincide control volume used to analyze the system. The density of a substance is the total mass of a substance divided by the total volume occupied by the substance mass per unit volume. Let us take a look at a video explaining the force.
So once again, guys, let's continue with the differences between force, mass, pressure, weight, etc. This time it's time to see the difference between force and pressure. They are very common misconceptions that force and pressure are the same. And yes, they are in a sense, because when we speak about pressure, we generally associate that to an area. And you know that this is a force, so that's why maybe you think that pressure and force and area are similar, but they are not. Let me show you why. Pressure is essentially a force applied to an area. Very important. Area is the key concept here. You may have a lot of force and a lot of area. You may have little force and little area. You may have high force, low area, and you may have low force and high area. Actually, there's a very important fact. If I were to ask you, what do you prefer, guys? Being stepped on by an elephant or being stepped on by a girl on high heels? And the fact is that a woman or this girl with her high heels might give you more damage than the elephant per se. Let me explain you why. Pressure by definition is force divided by area. It's directly proportional to the force. Okay, so if you increase the force, the pressure is increased. If you decrease it, the pressure decreases. But it's also indirectly proportional to area. So if you have area increases, pressure decreases, you are more relieved. But if you lower the area, you increase the pressure. So you have your area, you have the weight. If the weight is constant and you're changing area, well, you are going to change pressure. If your area is constant, but your weight is variable, you're also going to change the pressure. And I want to give you this example I showed you before. Imagine this girl is only 60 kilograms on weight. She has 2 feet, so we're going to divide that by 2. She's going to step you with this little area. This for you guys, it's about 120 pounds. Well, the girl has a mass of 120 pounds, okay? And this huge elephant, let's say she has this area, it's huge. Let's say that the elephant is 3 tons or has a mass of 3 tons, but the elephant has 4 feet. So you measure that and you will see eventually you make the division. The area of this is very small. The area of this is small, but not that small. And even though the elephant is huge, you will see that comparing 3 million versus 125,000, well, I rather be stepped on by an elephant than a girl with these high heels. And if you used to dance, especially in balls or something like that, weddings, clubs, whatever, you will see that if a girl steps on you with this high heel, will give you At least you will remember her till the rest of the night, okay? So hopefully you get the idea that the important here is the combination of force and area. And we're done with the definitions of force and pressure and all that. Next section, we're going to be analyzing mass flows, volumetric flows, and molar flow. What's up, guys? It's me, chemical engineering guy.
Again, we watch another video explaining force and gravity.
And why not? I'm going to show you what's the difference between force and gravity. Many people or many persons think that gravity is actually a force, but it is not. Gravity is the acceleration due to the gravitational force. Okay, so let me once again explain that. Force is by definition a mass that you accelerated. The units are typically newtons or kilograms per meter per square second. Now gravity, guys, is the acceleration due to gravitational force. So we have a force, actually in the earth, we have a force that is bringing you here. Gravity is the acceleration it has. So even though you have many masses, you will have different weights, the gravity is always the same. It doesn't care what type of material, how much mass do you use, the gravitational force is always the same. So we use that as gravity is an acceleration, meters times square seconds. So once again, be sure not to confuse force versus gravity. Gravity is an acceleration due to a gravitational force of Earth.
So we'll watch again the uh, video of thermodynamics properties, specific volume. Let us take a look at this video.
Specific volume is a thermodynamic property, and it's defined as lowercase v or lowercase Greek letter nu, and it's the ratio of volume to mass, or V over M. So that is our definition of specific volume. It can have units of meters cubed per kilogram, centimeters cubed per gram, feet cubed per pound mass. Essentially, we just have units of volume in the numerator and units of mass in the denominator. Now, specific volume is very closely related to density. Density is Greek letter rho, and density is the ratio of mass to volume. So it's exactly the reciprocal of the specific volume. So it's M over V, or 1 over specific volume. So in thermodynamics, something else to keep in mind is that this term specific is sometimes used to mean per unit mass. So anytime you have a property that's divided by mass, it's called specific. So if you have internal energy, it would be represented by capital letter U in many textbooks. And if you throw specific in front of that description, that gives you lowercase letter U. And so instead of units of kilojoules, now I have units of kilojoules per kilogram. So it kind of generalizes the problem because it's on a per unit mass basis. It's not tied to the particular mass of a problem. So why is a property like specific volume useful in thermodynamics? Let's see. We looked at another example where we said the density of water is approximately 1,000 kilograms per meter cubed. And it's important to note, this is liquid water. And we want to compare that with the density of solid water, or ice, which we'll say is approximately 920 kilograms per meter cubed. And so if I want to determine the specific volume of liquid water, then all I have to do is divide by the density. So 1 over 1,000 kilograms per meter cubed. So this gives me 0.001, and the units get flipped, so I have meters cubed per kilogram. And I can compare that with the specific volume of solid water or ice. So I have 1 over 920 kilograms per meter cubed. So that gives me 0.0011 meters cubed per kilogram. So you can imagine if I have 1 kilogram, this is like saying 0.001 over 1 or 0.001 over 1. So liquid water requires 0.001 meters cubed per kilogram of H2O. When it's in its solid phase, as opposed to the liquid phase, when it's in its solid phase, it requires slightly more space. It gets bigger. It expands. And this is something we've probably all seen, right? So water expands when it freezes. And this is actually kind of a unique property of water. A lot of substances don't expand when they freeze, they actually contract. Right, so why are properties useful and important in thermodynamics? And one thing that we can see from this example is that the properties are related to the phase of a substance. So the thermodynamic properties, and I'm going to just write properties for short. So the properties are related to, or I'm going to say they describe the phase of the substance. Describe phase. And phase is related to energy content. And phase change is related to energy transfer. And we know thermodynamics is all about energy transfer and energy transformation. For an example, let's consider a steam turbine. And it's usually kind of drawn like a megaphone in most textbooks, where you have, if this were the boundary line, then at the inlet, you have water as a gas entering the turbine, and that has some temperature, some pressure, some specific volume, and some energy content associated with it. And the turbine is going to convert the pressure and the energy in the gas into a rotational kinetic motion. And then usually that turbine is connected, it's got a shaft that rotates, and that's going to be connected to a generator. And the generator converts that rotational motion, that kinetic energy, into electric energy. And so we've got this energy transformation process, and it all starts with the water going through the turbine. And when the water exits the turbine, it's probably going to be a mixture of gas and liquid phases. And so this is really sort of illustrative of how phase and properties are related, because we can think of, we know the different phases. So solid would be ice, liquid, gas. These are the three phases of matter of primary interest in most thermodynamic applications. And these phases are sort of proxies for energy or energy content. So lower energy, lower temperatures are associated with solids, and as the energy increases, it's going to become a liquid. So if we're talking about water, it's ice, it'll melt, and then as you continue to add energy, it'll boil and it'll become a gas. So we have lower levels of energy associated with solid phases and much higher levels of energy associated with gas. And we use thermodynamic properties to help determine the phase and the energy content of whatever the substance is that we're using to help transfer energy.
So we will watch again the other video explaining the density.
Which is heavier, a pound of feathers or a pound of bricks? This is a classic trick question, and I'm sure you know the answer to it. They each weigh a pound, and so they are the same weight. But there is something different about a pound of feathers and a pound of bricks. A pound of feathers will take up much more space than a pound of bricks. But why is that? Well, a pound of feathers would be much less dense than a pound of bricks would be. Density relates two units that are commonly used to describe matter: mass and volume. Remember that mass is a measure of the amount of matter, or how much stuff there is, and volume is a measure of how much space that matter takes up. When we put these units together, we come up with density. And so density is the amount of matter per unit of volume. And we could calculate density using the following equation. Density is equal to the mass of an object divided by its volume. Let's compare a substance with a high density to a substance with a low density. Air has a very low density. If we had 10 grams of air, we would have over 8 liters of air. Remember that grams is a measure of mass, and liters is a measure of volume. And so 10 grams of air would be enough air to fill over 10 2-liter pop bottles. Now let's consider a highly dense substance. What if we had 10 grams of lead? 10 grams of lead would occupy less than 1 cubic centimeter of space. Just a side note, when we're working with solids, we usually use centimeters cubed as a unit for volume instead of milliliters. Just so you know, 1 milliliter is saying the same thing as 1 centimeter cubed. And so we use centimeter cubes when we're talking about solids. And we use millimeters when we're talking about liquids and gases. Okay, so how much space does 10 grams of lead take up? Well, we could fit 10 grams of lead into a small nail. Here we have the exact same mass as the 10 grams of air, and yet it's taking up much less space. And so we could say that lead is much more dense than air. Let's try calculating density based on some measured values. Remember our equation for density. If you had a cube of copper, that had a volume of 16.7 cubic centimeters and a mass of 150 grams. What is its density? Using the equation above, we can see that density will be equal to mass divided by volume. And so the mass is 150 grams divided by the volume of 16.7 cubic centimeters. We'll see that the density is equal to 8.98 grams per centimeter cubed. And that's our final answer. Let's try another one. This time I'll give you the density and the volume, and you'll find the mass of the object. Here's a bucket filled with seawater. The density of seawater is 1.027 grams per milliliter. And this bucket has a volume of 15 liters. What is the mass of the seawater? The first thing we should do is write down the equation that we're going to use. The next thing I want to do is just double check that all my units are in SI units, or at least agree with each other. If I take a look at my units for volume, I can see that liters are listed here and milliliters are listed here, and I need to have a common unit. Since my density is usually measured in milliliters, I'm going to convert the 15 liters into milliliters first. To do that, I'll multiply by a conversion factor that compares milliliters to liters. There are 1,000 milliliters for every liter, and I can see my liters will cancel out and I'll be left with milliliters. And so 15 liters is the same as 1.5 times 10 to the 4 milliliters, or in other words, 15,000 milliliters. Now that we have like units, let's rearrange our equation so that mass is isolated on one side of the equation. To do that, I'll multiply both sides by V to move V to the other side of the equation. Now volume will be canceled on the right side of the equation and be left over here on the left side of the equation. Let's rewrite this equation now. And so mass is equal to density times volume. As I can see, I flipped the equation just to make it look a little bit nicer down here. Let's plug in the numbers and solve. We can see that milliliters will cancel and we'll be left with grams, which is what we want for mass. Here's our final answer, 1.54 times 10 to the 4 grams. We can also see that we have the correct units, and we also have the correct number of significant figures. In our answer here, we have 3 significant figures, and our least significant measured value was over here with 1.50 times 10 to the 4, which is also 3.